Welcome back, everyone. In this video, we're going to continue our discussion of electromagnetism, and specifically, we're going to be talking about Lenz's law. So, which direction does the current go when we have an induced EMF? We're also going to be talking about motional EMF, which occurs when a conductor is in motion through a magnetic field. So first, let's start with another example problem, and we have a loop of area A that's placed in a region where magnetic field is perpendicular to the loop, and the magnetic field will be changing as a function of time. So we want to find the function defining the EMF of the loop, and we want to find the value for this at 4 seconds. So we know that EMF is going to be equal to negative d flux dt, and in this case area will be constant, and we'll need to calculate dB dt. Okay, so the tricky part is that we have a function for the field that has an exponential to the minus 1 over t. So when we calculate the derivative of that, so d dt of b max e to the minus 1 over t, a couple things happen. First of all, the b max comes out of that, but then secondly, if we have e to the x, the derivative of e to the x is just simply e to the x. So this is a chain rule where we're going to have to just write the function itself, e to the minus 1 over t, times the derivative with respect to time of that function. So if you've studied the chain rule in calculus yet, you will have seen this. So that's d dt of negative 1 over t. And so the result from this is we're going to get negative a b max e to the minus 1 over t simply over t squared. So the derivative of negative 1 over t is 1 over t squared, because if you think about it, negative t to the minus 1 turns into double negative t to the minus 2. Okay, that means that our EMF is going to have this function, and when we evaluate it for t equal to 4, then we're just going to have negative a b max e to the negative 1/4 divided by 16. And if we knew values for a and b max, we could plug that in and we'd be all set. Okay, but the main topic of today's lecture is Lenz's law, which states that the current is going to flow in a direction so as to oppose the change in flux. We're going to use this with the right-hand rule to predict the current direction. So this is going to be our third right-hand rule. And it's a lot easier to do if you draw the induced magnetic field that results from the changing magnetic flux. And actually what I suggest is drawing it from kind of a side view. So I'll show you a couple of examples of what I mean. Okay, so in this problem, we have a magnetic field which is increasing at a rate of 4 milliteslas per second. We want to calculate the direction of the current in the wire loop. So the field is coming out of the page, but it's also coming out of the page more. Okay, so what I suggest is drawing a side view. So the loop just looks like a line. Okay, it has no thickness. And we would say that this is sort of out of the page on this side, and this is kind of into the page on this side. Now let's draw what the magnetic field is doing to begin with. That would be B initial. It's coming out of the page, but it's also increasing. So that means that if I drew B final, it would be coming out of the page more. This means that the difference, or how much the magnetic field has changed, is also out of the page. Now, Lenz's law says that there will be an induced field, B induced, which will be exactly opposite to the change in the magnetic field, to cancel out the change. In other words, nature is going to kind of bring the system back to equilibrium before there was this change. And so that means that the induced field can be drawn as going into the page. So induced field is going into the page. Now, the third right-hand rule is going to state that our thumb is going to be the direction of the induced field. Then the curl of our fingers will represent the direction of the current. And if we do this, we see that you point your thumb into the screen, and we're going to see that the current is going to be going, as we said previously, clockwise for a negative induced field. So if the field is going into the page, which is induced, we get a clockwise current. Okay, so the direction here is clockwise. Let's try another example. So now the magnetic field is increasing at a rate of 4 milliteslas per second. We're going to do the same thing. The field starts by going into the page. So we draw our side view. We have out of the page and we have into the page. And we start with this field going into the page. Now, the problem isn't quite clear, but let's say that when it says the magnetic field is increasing, that it's going into the page more. So if that's B initial, then B final is even more into the page. And this is just the opposite of what we had on the last slide. So this delta B would be going into the page, which means that the induced field would be coming out of the page. Okay, so B itself is the X, but B induced is coming out of the page. Now, your thumb is going to point out or towards you, which means that now we have a counterclockwise current. Okay? And so this is really all there is to it when it comes to Lenz's law. And if you think of things in this term where you sort of look at it from the side and draw what's going on, it's a lot easier to visualize. Okay, so now let's try one more problem where we're asked to find the magnitude and direction of the current. So we'll start with the magnitude. So we know that this is going to be EMF over R. So it's going to be 1 over R times negative d flux dt. And in this case, the field is decreasing and the area is constant. So it's going to be negative A over R times dB dt. So we plug in everything, and that's going to be negative pi 3 squared, pi r squared. Resistance is 4 ohms. And dB dt is going to be negative 4 times 10 to the minus 3 teslas per second. Now this is important that you have a negative sign when it's decreasing. dB dt can be plus or minus. And when you calculate this out, you're going to get I is equal to 28.3, thereabouts, milliamps. And it's got a positive sign. And let's think about this. We said that a positive sign denoted a counterclockwise induced current. So let's see if that's correct using Lenz's law. So we start by thinking about the initial field, which is coming out of the page. And now the magnetic field is decreasing. So B final is going to be less, which means that the change is pointing into the page, and therefore the induced field to offset that change will come out of the page. Okay? So that means that the induced field will come out of the page. If you want to think about it another way, this induced field is kind of restoring the final field back to where it was. And because of this, put your thumb pointing out at you. Your fingers are going to curl in the counterclockwise direction, which we are saying is the positive direction for current if you're using Faraday's law in conjunction with Lenz's law. Okay, so the last thing that we're going to look at is a concept called motional EMF. Now, motional EMF is given by EMF equals BLV, where B is the magnetic field strength, L is the length of the bar or a wire, and V is the speed. And what we're going to try to do is to quickly derive this expression. So what we want to do is draw a little picture. So here is the typical situation that you'll see. You'll see a bar or a wire which is sitting on another wire, etc. And it'll be in a uniform magnetic field. And it's going to be moving with some speed v. Now we could say that this speed is actually dx dt, and that means that the distance it travels in a small amount of time, dx, is going to be equal to v dt. So if a little bit later the bar is over here, we could say that that distance is dx, which is v dt. Okay. Now if the bar has a length of L, then that means that dA is going to be L, the length of the bar, times dx. Or in other words, A is LV dt. Hopefully you can see where we're going with this. That's where the LV comes into this. Now we just use the definition of EMF, and we're just going to do magnitude. So it's d flux dt, and in this case B is constant and the bar is moving, so we have dA dt. However, we just said that dA was actually equal to LV dt, but we must divide that by dt, which goes away, and there we are. There's our expression for EMF. Cool. And you're going to have to take my word for it, but if you multiply out all these units, you will get volts. So I'm not going to do that right now, but I did it with the other one. Okay, so here's one example, right? How much current is going to flow through this resistor, and how much power is dissipated by the resistor? So first, we're just going to find the magnitude of the current, which is EMF over R. EMF we said is BLV over R, so we just plug in our values, 0.15 Tesla, L is 0.50 meters, V is 2 meters per second, and so by the way, as an aside, you can see that the EMF is 0.15 volts. Okay, we'll need that a little bit later. And the resistance is 3 ohms, so that means that the current is 0.05 amps. Okay, and how much power is dissipated by the resistor? Well, P is VI, which in this case is EMF times current. And if you look at this, we have an EMF of 0.15 and a current of 0.05, that's 0.0075 watts. But you could also say that because it's equal to EMF times current, current is EMF over R, so it's E squared over R, which is B squared L squared V squared over R. And sometimes you'll see that. Okay, now, last thing. What direction is this current flowing? So to do this, we need to apply Lenz's law. And first we note that the field is going into the page to begin with. So this is out of the page, and this is into. So it starts out going into the page, and here's where it gets a little bit weird. Instead of saying that this is the field, it's probably easier to say that this is the flux initial. And this is because the area is changing. And what we can say is that after the bar has moved a little bit, there's going to be more area. So the total amount of flux is greater going into the page. So flux final is bigger. which means that the change in flux is also into the page, which means that the induced field must be out of the page. So there will be an induced magnetic field coming out of the page, and if we do the right-hand rule with this, your thumb comes out at the page and the current is going to be going down through the resistor from point A to point B. Okay, now the last thing to point out is that there's actually a force on this rod. There's a magnetic force because F is equal to IL cross B. And because the current is going up, remember we point our fingers that way and we point our palm out of the page for the magnetic field, and then what we get is, we want to use the, let's see here. We want to use the field from the background. So we're going to be using the field that's going into the page. So this just means that the current is going up and you have to point your palm so it's pointing into the page, and then that means that there's a magnetic force pointing to the left on this bar. And this is another way of saying there's no such thing as a free lunch, because you have to have some sort of force which is opposing the forwards motion of this bar. Otherwise it would be a source of free energy. Okay, so that wraps up our discussion of electromotive force and Lenz's law. And next time we're going to be looking at electromagnetism and Faraday's law in a little bit different way. We're going to be looking at this from the perspective of the electric field.